Welcome. This is the stuff that separates developers who write C++ from developers who understand C++. A concept is a contract. Before the compiler even looks at your template implementation, it checks, does this type satisfy the deal we agreed on? Type traits are compile-time queries. They tell you what properties a type has. Together, concepts and traits let you write generic code that's clearer, safer, and produces better error messages. Let's get into it. Traditional templates often fail with long, unreadable error messages that point deep inside the implementation. Concepts fix this by declaring what a type must support up front. Here we define a printable concept. The type must support being streamed to cout. Then we constrain the function, template printable t. If you pass a type that doesn't support streaming, the compiler rejects it at the call site with a clear message. This type doesn't satisfy printable. No more scrolling through pages of template instantiation errors. The constraint is readable, the error is local, and the intent is documented in the code itself. You can combine concepts and compile-time expressions to build richer constraints. Small integral requires that t is an integral type and that its size is 4 bytes or less. Sortable value requires that t is totally ordered and that it's movable. These composed constraints communicate design intent. The name sortable value is more meaningful than a raw conjunction of type traits. Good concept names read like design vocabulary. Printable, sortable value, reservable range. Not like implementation trivia. Let's build a concept you'd actually use. Reservable range requires 3 things. The type has a reserve method taking a size, and it has begin and end methods. This describes containers like vector and string that support pre-allocation. The function pre-allocate-like is constrained to reservable range. If you pass a type without reserve, the compiler rejects it immediately with a meaningful message. The concept moves the error to the boundary and documents the requirement. Here's what concepts look like in real code. We define validatable. The type must have a validate method that takes no arguments on a const object and returns a bool. The compound requirement syntax lets you specify both that the expression is valid and what it returns. The function allValid takes a vector of validatable types and loops through them. If any element fails validation, we return false. The concept expresses the contract once. The algorithm stays small and obvious. Concepts and type traits serve different roles. Concepts answer the question, may this type be used here? They belong at the interface boundary, public function signatures, class template parameters. They're readable and self-documenting. Type traits answer the question, what property does this type have? They belong inside the implementation. Compile-time branching, type transformations, internal logic. Use concepts at the boundary to constrain what comes in. Use traits inside to inspect and adapt. Here's where traits shine. Internal branching. This function log_kind accepts any type. Inside, it uses if constexpr with type traits to branch at compile time. If t is floating point, it prints floating point. If t is integral, it prints integral. Otherwise, it prints other. No concept is needed at the interface. The function accepts everything. The traits handle the specialization internally. 5 type traits you'll use constantly. Is same v. Checks if 2 types are identical. Is integral v. True for int, short, long, char, and their unsigned variants. Is invocable v, checks if a callable can be invoked with the given argument types. Remove cvref t, strips const, volatile, and reference qualifiers to get the underlying type. And conditional t, a compile-time ternary that selects between two types based on a Boolean condition. These 5 cover the vast majority of trait-based generic programming. If constexpr is compile-time branching that only compiles the matching branch for each type. In this describe function, if t satisfies the integral concept, we print integral. Otherwise, we print non-integral. When you call describe with an int, only the first branch exists in the generated code. This is cleaner than tag dispatch. Use if constexpr when the branching logic is small and local. When a constrained template fails, the error message points at the concept. But you can make debugging even easier with 3 practices. First, give important constraints names. Stream insertable is easier to diagnose than an inline requires expression. Second, check the first failed requirement. It's usually the root cause. Third, build helper concepts for patterns that appear repeatedly. Named concepts are both documentation and diagnostic tools. 3 rules for combining concepts and traits in practice. First, use concepts to state what callers must provide. They belong in function signatures and class template parameters. Second, use traits to inspect type properties inside the implementation. They help you adapt behavior without exposing complexity. Third, use if constexpr when one generic function only needs a few type-based branches. Concepts at the boundary, traits inside, if constexpr for small branches. 3 exercises to practice. First, write a concept that requires pushback and size. Then, constrain a function that only works with containers supporting both. Second, write 2 overloads, one for integral types and one for floating point, using concept constraints. Third, find a trait-heavy helper and wrap it in a named concept that expresses intent. For next topics, continue with concurrency for threads and async. Then, advanced ranges and views for composable, lazy operations. You now understand the constraint system. Use it to make your generic code speak clearly. Thank you.